Okay, so this is for periods 3 and 4. It should be Friday. This is our last lesson on probabilities and statistics in general. So, last lesson within the unit, 6.4, probabilities of dependent events, which is the exact same thing as conditional probability, it just retitled a different way. It's just another day of conditional probability. Different types of things going on today, though. So quick warm up, if you want to pause the video, I want to know the probability of selecting two aces in a row from a standard deck of playing cards with and without replacement. All right, so if you've got the answer already, if you think about two aces from a standard deck of playing cards, right, there's total out of uh, four aces out of a total of 52, which is 1 out of 13. So if you replace the card, right? You had 4 out of 52 times, if you put it back in, it's another 4 out of 52. So it's 1 out of 13 times 1 out of 13, which is just 1 out of 169 chance, right? Not good. Now, if you don't replace it, so if you take out the ace, right, the first card that you get is still a 1 out of 13 chance that you'll get an ace. Now, it's really 4 out of 52 if you think about it. It just reduces to 1 out of 13. So it's 4 out of 52. But if you didn't replace the card, then the probability you draw another ace after that, right, means there's only three favorable outcomes left. There's only three aces left, and there's only 51 cards left. The sample space changed, but so did the number of favorable outcomes, right? And it's not the same thing as 4 out of 52. It's a different ratio, even though they both went down by one. It's not the same probability. So basically, this one would be a 3 out of 13 times 51, whatever that number is. 13 times 51, 663, which is, we just hit our fraction button, math, oops, fraction, and it should be 1 over 221. That's weird. Oh, I need to do 1 over that. But you can do it in your head probably. 663 divided by 3 is just going to be 221. It's the 1 out of 221 chance. It's even less, which should make sense, right? If you did draw an ace the first time, well, now there's even less aces out there. Yeah, the sample space is smaller, but it's only smaller by 1. Not really getting that great of odds. So that's why 1 is 1 over 169, 1 is 1 over 221. Still not good odds either way, but it's even worse if you don't put the card back, right? You're not putting the ace back. It means only 3 left instead of 4. All right, so with dependent events, always remember that the number of favorable outcomes in sample space is changing. Just like that last example, that would be dependent because the probability that the first one happens is affecting the probability that the second one happens, right? If you draw an ace, you have now affected the probability that the second one's going to happen, right? Even if you didn't draw, you'd still be affecting the probability that the second one is an ace. But that's not true for independent events. Like the first one I did, when you replace the card, those are independent because it's the same amount of favorable outcomes, 4 out of the same sample space, 52. There's no change, they're independent. So let's look at this one, right? So you and two friends go to the same store at different times to buy costumes for a costume party. There are 15 different costumes at the store, and the store has at least 3 duplicates of each costume, which all that means is that, you know, if you go and your friend goes and your friend goes, you could actually all have the exact same costume because there's at least 3 duplicates of everything, right? So what's the probability that you choose different costumes? Well, it should be pretty good, right? There's 15 to choose from as long as and you're not talking to each other, but as long as you pick different ones, you'd be okay. So it's what we call the probability of A and B and C, right? So in that case, you're going to multiply the probability of A times the probability of B given that A has happened, right? Times the probability of C given that A and B have both happened, right? So essentially, again, it's a number of favorable over a number of possible. This looks like a pretty heavy formula, but it should actually kind of make sense when you think about it. The first one is just the probability that A happens, right? So the first person goes, what's the probability that she picks a different costume than everybody else? Well, she's the first person to go. It's 100%, right? She has to pick a unique costume. So there are 15 favorable outcomes out of the entire 15 outcomes, right? As long as she picks a costume, it's favorable, right? Because it's unique. Now, the probability of B given A, now given that A has already happened, somebody has picked a costume, what is the number of favorable outcomes now, right? Well, there'd be 14 favorable outcomes because there's one costume that you don't want to pick. Whatever person A had, person B does not want that same costume because that would not be favorable because it wouldn't be different. But because there's duplicates of every costume, there's still 15 in your sample space. That person could still pick one of 15 things, just that one of those things, whatever this person picked, would be not favorable, right? And the probability of C, given that A and B both happen, is the probability that this person would pick a unique costume given that these two have already picked theirs. Well, basically, there would only be 13 costumes now that would be unique or different. And even if these two people pick the same one, there would still be 15 costumes to choose from because there's 3 duplicates, right? So the probability of A times the probability of B given A times the probability of C given A and B is simply 15 out of 15 times 14 out of 15 times 13 out of 15, right? 15 out of 15 is just 1. So it's really just 14 out of 15 times 13 out of 15, which if you did that on your calculator, 14 out of 15 times 13 out of 15 is 80.9%, right? It's pretty good. It's not for sure. It's not certainly a certain event, but it's pretty good percentages that you would pick. You would all have something different, right? God forbid you showed up to the Halloween party or the costume party and were wearing the same thing. That would pretty much end your reputation at Duxbury High School as you know it. So you should be safe, right? 80.9, is pretty good odds. All right, so on your own, you can pause the video after you read it, but you have 4 questions here. These are all based on a standard deck of playing cards. You're not replacing the cards, right? So you can think about it, they are dependent. If you're not putting the card back, that means the probability of one is affecting the other. So go ahead and pause the video, and then when you're done, you can resume it and then check your answers. All right, so if you finish these, the probability of drawing a face card, there's only 3 face cards per each suit, king, jack, and queen. Ace doesn't count as a face card. It's not a face on it. But the probability of you drawing a face card, right, there's essentially 3 in each suit, and there's 4 suits, so there's 12 face cards total out of 52. Or if you just think in terms of each suit, which same thing as 3 out of 13. Okay? So the 3 out of 13% chance, or 3 out of 13 probability that you draw a face card. Then a 6, so followed by a 6. But if you think about a 6, there's 4 6s, 1 in each suit. So there's 4 favorable outcomes. However, if you didn't replace the card, there's only 51 cards left. So it's 3 out of 13 times 4 out of 51, which I have as a 1.8% chance, assuming I did that correct. 29, a 10, right? There's 4 10s out of 52, which you can reduce, but if you have a calculator, you can just use that. And then a 2, well, there's 4 2s, but there's only 51 cards left. So it's 4 of 52 times 4 of 51, which gives you a 0.6% chance, I believe, if I did that correct. The next one, a king, and then a queen, and then a jack, right? Kings, 4 of them out of 52. A queen, 4 of them. but it's conditional probability, so there's only 51 cards left. And then a jack, there's 4 jacks, but at this point you've already drawn 2 cards, so there's only 50 left. So again, number of favorable over possible. Favorable, possible, favorable, possible. And if you did that right, I think you get very small odds. 3 different things happening. So it's 0.05%, I believe. And then last but not least, a spade and then a club and then another spade. Again, it's 3 things, but actually there's a lot more favorable with if you're just talking suits. Right? A spade, there's 13 spades out of 52, which is the exact same thing as 1 out of 4, right? Just reducing it. I didn't reduce some of these, but same thing. And then a club, well, there's 13 clubs, but there's only 51 cards available if you just drew a spade. And then another spade, right? Well, if you drew a spade first, that went from 13 down to 12. And again, the sample space is going to be down to 50 since you've already drawn 2 cards. So if you did all that, that would give you a 1.5% chance. Still not good, right? But that's how you should do those ones. All right. And then the second part, which is really probably the most new thing, is going to be probability tables and trees to kind of figure out different probabilities and read them from some of the information that's given to you. So like this is a tabular representation of data, right? It's saying it shows the number of tropical cyclones that formed during the hurricane seasons from 88 to 2004, right? So A, estimate the probability that a future tropical cyclone is a hurricane, which would just be the probability of hurricane given that it's probably the future is a hurricane. All right, never mind, sorry. And the probability that a future tropical cyclone in a northern hemisphere is a hurricane, right? So if we think about this one, we're going to look at A first. So it's the probability of just having a hurricane, right? The probability that a future tropical cyclone, everything is a future tropical cyclone here, is a hurricane. So it's really just going to find the probability of a hurricane. So take the number of favorable that you have, the number of hurricanes. Well, that would be in the row of hurricanes. So 545 and 215, that's going to give you the 760. So there's 760 favorable outcomes. And then out of the sample space, which would be the whole entire thing. So if you added up all these numbers, you would get 1575. So 760 is hurricanes, 1575 is all the cyclones, including the hurricanes. That would be your entire sample space. You get about 48.3%, right? Now the probability that a future tropical cyclone in the northern hemisphere is a hurricane would actually be the probability of a hurricane given, like what we did from 6.3, that you are in the northern hemisphere, right? So I think that's what this is going to say. Probability of hurricane given you're in the northern hemisphere, which, if you remember from the formula, it's the probability of both hurricane and northern hemisphere divided by the probability of just northern hemisphere. Number of favorable, sample space, right? So the probability of hurricane and northern hemisphere, or in the northern hemisphere, it's the same thing, would literally just be the one cell where it's northern hemisphere and hurricane. They both meet right there, 545. That's the probability of both happening, hurricane and northern hemisphere, right? So that's the numerator. The denominator is the entire sample space of northern hemisphere. So 199 plus 398 plus 545 is going to give you the 1142. So you have, again, probability of A and B over the probability of just B, right? Probability of hurricane given northern hemisphere, probability of both over probability of northern hemisphere, and it's basically 545 over 1142, which is 47.7%. Okay? A different type of representation is a probability tree. So this example is using high school drivers in situations where the adults wear a seatbelt and they don't wear a seatbelt. So the question is going to ask, it kind of gives you this information. A high school student, I'll actually start with this one. A study reports that 69% of adults wear seatbelts, right? So here we go. We have adults wearing seatbelts. 69% wear seatbelts, 31% do not wear seatbelts. Obviously, if 69% do wear seatbelts, didn't give you this, but you can figure it out. It's basically the complement to this. Uh, it also says that students wear seatbelts 66% of the time when the adult wears a seatbelt. It seems low, but whatever. So 66% of the time the student wears a seatbelt given that the adult is wearing the seatbelt, which means that 34% of the time they don't wear the seatbelt given that the adult does wear the seatbelt. And then the last piece of information just says 26% of the time the adult does not wear a seatbelt. Students do not wear a seatbelt 26% of the time when the adult does not wear a seatbelt. So you see here, 26% of the time that an adult does not wear a seatbelt, the student still does, right? But it also means that obviously 100% minus 26%, 74% of the time, the student does not wear a seatbelt if the adult does not wear a seatbelt, right? Apple doesn't fall far from the tree. So what is the probability that a high school student wears a seatbelt? So it's really just a probability of event C happening, right? There's just two ways to get there. So this is where we're going to introduce the word or, right? It's kind of the probability of event this or this one, but it's just titled C, but there's two ways to get there, right? So what we're going to see is the probability of A and C plus the probability of B and C. So we have the probability of A and C and the probability of B and C. And you would add these two things together. But basically all you do is you just multiply the pathway. So it's 0.69 times 0.66. That would give you the probability of a student wears a seatbelt given the adult wears a seatbelt. And 0.31 times 0.26, which would be the probability a student wears a seatbelt given the adult does not wear a seatbelt. And that's really it. So again, you have the probability of A happening times the probability of C happening given that A has happened, plus the probability of B happening, 0.31, times the probability of C happening given that P is happening. Those are the two pathways for your favorable outcomes, and all you do is simply multiply the numbers. So you have to get to this student wearing a seatbelt from the adult, it's 0.69 times 0.66, plus there's another favorable way to get the outcome, 0.31 times 0.26. So overall, you get 0.536, so there's a 53.6% chance that a high school student in this study is actually wearing a seatbelt, which that seems very low, but that's what the data says. And what I want you to do now, you don't have to do it in partners, but I want you to pause the video and try and do these questions. So it's basically a two-way table of people who like Mario or Zelda video games and basically their sport preferences. And try and do the best you can, and then I'll go through them after you're done. All right, so here we go. We have the probability of Z, which would be the probability that somebody likes Zelda. So, probability that somebody likes Zelda, well, there's 77 people who like Zelda if you added up all these columns. And this one's nice because it actually gives you the total, unlike the hurricane one that I gave you before. But basically, there's 77 people out of 159 people that like Zelda, right? So 77 over 159 is 40.48, so 48%. And that's all you need to do. The second question, what is the probability that somebody likes Mario and football? Well, probability that somebody likes Mario, right? This is the Mario row. This is the football column. So probability that somebody likes Mario and football is just simply 22. You just look at the one cell. 22 out of the 159. So 22 out of 159 is about 14%, right? So that's the probability that somebody likes both of these things. Now here we go. We have the probability of Mario or Zelda. What is the probability that somebody likes Mario or they like Zelda in this study? Well, this is an interesting one because they have to like one or the other. There's no third choice here. It's probably that they like Mario, which is 82 people, and then the probability that like Zelda is 77 people. So the probability that somebody likes one or the other is going to be 82 plus 77. That word or almost signifies addition, right? There are two favorable outcomes. 82, well, two different types of favorable outcomes, I should say, right? But one of them's 82 and one of them's 77. That's going to add up to the 159. So the probability that somebody likes Mario or Zelda is 100%. Everybody likes Mario or Zelda in this study, right? They have to like one or the other. Same thing with this one. We have in the or, the probability that somebody likes football or soccer. Well, the probability that somebody likes football, right, you can just look at the total, is 38 people, right? So you're going to have 38 people for football. Oops. And the probability that somebody likes soccer is 30 people, right? So there, again, it's that word or signifies that both of these are favorable outcomes. So essentially just add them. It's 38 out of 159 plus 30 out of 159, which would give you 68. 68 out of 159, right? So you would add those two together. That word or is kind of signifying adding because there's different favorable outcomes, but they're both favorable. So you add them up. So 68 out of 159 gives you about 43%. Now here's where we're getting into the stuff from last class. The probability that somebody likes Mario given that they like baseball, right? So the probability of somebody liking Mario given that they like baseball. We can do the whole formula part, but we can probably just get it right from the table itself too if we can make sense of it, right? Given that they like baseball. So if we're given that we like baseball, we are essentially looking at the baseball column. So like given that they like baseball, just stay in this column because they have to like baseball. So what's the probability that they like Mario given that they like baseball? Well, the probability that they like Mario in this column is 19. That would be the favorable outcomes out of a total of 42 outcomes. So it's 19 people who like baseball like Mario. So the probability that somebody likes Mario given that they like baseball is 19 out of 42, which is 45%, right? The other way you can do it is the probability, the formula is the probability of both. So M and B over the probability of just B. That would give you the probability of M given B. So the probability of M and B, right? Well, M and B would be 19 out of 159. Oops. Divided by the probability of just B, which is 42 out of 159, which instead of dividing, you can multiply by the reciprocal, but basically the 159s would cancel. You'd get 19 out of 42, just like we did reading from the table. So it's maybe a little easier and a little less work to just kind of get it from the table and understand what this means. But if you're more of the algebraic type and you just want to see it out done with math, it does still work, but it's just more work for you, right? Probability of baseball given football. So the probability that somebody likes baseball given that they like football. Well, this one's a little different, right? How can somebody like baseball given that they like football, right? They like one or the other. So hopefully that one was kind of a head scratcher. But the probability that somebody likes baseball given they like football, it's not 100% like this one was. It's not, or it's zero, right? You can't like both in this study. So the probability that you like one given the other doesn't make any sense. There's 0 people who like baseball given that they like football. They have to like one or the other, right? Now estimate if events Z and B are independent, right? Good question. So how could you figure out if events Z and B are independent? Well, if they're independent, that means the probability of Z given B is equal to the probability of just Z. which would mean B has no effect on Z. Right? Z given B is equal to just Z. Well, then B had no part in influencing it whatsoever. So again, you'd have to kind of do this work, but the probability of Z given B, we'll look at this, the probability of Z given B. You could use the whole formula, or you can just look at the table, right? The probability of Zelda, given that they like baseball. So we're actually still in this baseball column, but now we're actually looking at the 23. So the probability that somebody likes Zelda, given baseball, is 23 out of all the baseball is 42. So we got 23 out of 42. 23 divided by 42, right? 54.76, 54.8%. So basically what that means is if that's equal, right, that's the probability of Z given B. That's over here. Now the probability of Zelda, which we had already before, it was just this one up here, is 48%, right? So we have 54.8% comparing it to 48%. Well, all of a sudden, these are definitely not independent. So the answer is no, simply because they are not independent, right? Because the probability that you like Zelda, given that you like baseball, which was the same thing we just had, it was 54.8%, that is much higher than the probability that you like Zelda on its own. So for whatever reason, the people who like baseball tend to like Zelda a little bit more than the people who just like Zelda in general, right? And they're in that population too, but for whatever reason, your liking baseball is actually increased the probability that you would like Zelda, right? So they're not independent of each other, right? Now, if we look at Zelda and running, see if those are independent, again, we would kind of have to do the same thing we just did. We'd want to find the probability of Zelda, given that they like running. You could do it the other way around too, running giving Zelda. You actually want to do it both ways to prove independence, but we'll do it this way first. And we're going to see if that's equal to the probability of just Zelda, right? Which in the last case it was not. Here we'll take a look. So the probability of Zelda given running. All right, so we're going to look at the running column. We're going to say, okay, the probability that somebody like Zelda, given that they're in this column, is 24 out of 49, right? So 24 out of 49 is the probability that somebody likes Zelda, given, or 49, given that they like running. We got 24 out of 49, which is 48.97, so just under 49%. And then if you just looked at the probability of Zelda, which we already had before, was 48%. So as I said before, hopefully I said it before in class, if the two events are within 1% of each other, that's going to be our cutoff. So that's 48%, right? It was 77 out of 159. We can get it down to a decimal. 77 out of 159. That's the probability of Zelda, right? 48.4, 48.97. These are within 1% of each other, right? If you converted it, if you move the decimal over to, they're within 1% of each other. So for our purposes, we'll say that they are actually independent. And they're not exactly the same, but they're so close that we're going to say that they're independent, right? So this is, these are independent in this sample, right? Now to prove it, you should also do the probability of R given Z. Make sure that's equal to the probability of R. But again, it's like 6 divided by 2 is 3, and 6 divided by 3 is 2. If it works one way, it will work the other way. You just want to show both on tests and quizzes to make sure that you're kind of applying the definition of independence in your proof. All right, so here we go. Last example, you don't have to do it in partners, you can just do it on your own, but I want you to make a tree diagram, which is kind of like the one we did before, something like this. It's called a tree diagram or probability tree. Make a probability tree using this information. You can pause the video, and when you're done, start it back up. All right, so I'm going to make a tree diagram here, and we're going to go this way and this way. I'm going to move this actually. So a high school basketball team leads at halftime 60% of the games, right? So I'm going to start with that because that's the first piece of information that I can use. So 60% of the time, so 0.6% of the time, they have the lead, right? Which all that means is 0.4, 40% of the time, they are losing, right? Or tied, I guess. We'll just say losing, but you could say that they're tied. We'll just kind of group those two together because this says lead, and that really wouldn't throw up anything else. Okay, so they win 80% of the time when they have the lead. So if I wanted to take this, I could break this into two ways. If they have the lead and they win or lose. So here, 80% of the time when they have the halftime lead, they win. So zero point 0.8, they get a W, right? They win the game. Which just means that even though they're leading 20% of the time, when they're leading at halftime, 20% of the time they actually still lose the game, right? And then the last piece of information just says that they win only 10% of the time when they do not have the halftime lead, right? They fold like a cheap 10. So only 10% of the time they will actually pick up a W despite losing, despite winning, despite losing at halftime, right? Which just means 90% of the time, if they're losing at halftime, they're going to get the loss in the final, at the end of the game. So what's the probability that a team wins a game during this season, right? So again, all you would want to do is just kind of multiply the pathways that give you favorable outcomes, which would be a win and a win, right? So it's probability that they win given they have the halftime lead plus the probability, and then, whatever times the probability that they have a halftime lead plus the probability that they win given the fact that they're losing at halftime times the probability that they're actually losing at halftime, right? So in this case, it would be just 0.6 times 0.8 plus, right? That's almost like or, you have two different types of favorable outcomes. 0.4 times 0.1. And I think when you add all those two together, you get something like 52%, right? And that would be the probability that they win a game. All right, so quick summarizer. If you think about this, when is it preferable to use a tree diagram instead of a table? When is it preferable to use a table instead of a tree diagram? Um, you can think about it and then just kind of brainstorm ideas and then resume the video. But, I would say when you want to use a tree diagram for things like this, it's almost sequential. It's this happens and this happens. Or the basketball, and they get the lead and then they win. They're not winning and then they win, or something like that. So, I kind of had something like sequential when things follow order or probabilities are affected based on other things happening. But it's usually like time is passing in a lot of these questions. Um, and then also with these ones, there's also multiple ways to get a favorable outcome. A lot of times that has to do with tree diagrams as well. So in both of the examples, right, there's two ways to get a W here, whether you're winning or losing at halftime. With this one, there's two ways for a student to have a favorable outcome wearing a seatbelt, whether the adult does or not. But with a table, it's almost like, I think the only example we had were the Hurricanes and the Mario and Zelda ones. But it's usually when you have like categorical data, right? So when you have different categories of data and you can compare them across each other with something like a two-way table, that's usually going to signify using a table, right? And you kind of see more of these. You get a couple more in the homework and the activities. So you get more comfortable at figuring out what would be better to use and what would be more difficult to use. But that's the end of everything that I kind of wanted to have covered today. What you guys are going to do now is basically, now the 6.4 notes are done, summarizer's done, you guys can just start the homework, which is a 6.4 worksheet, which is on Schoology.